Hi everyone, this is Dr. Hopkins recording the last of our series of videos on gases. It's our third for 472. So if you recall the last video, we talked about the ideal gas equation. We went through all of the assumptions behind the ideal gas equation. And so what we're going to do at this point is what would we need to do if we know a gas is not behaving ideally, or better yet, if we know we need to know the pressure or volume of the gas much more accurately than the ideal gas equation will give us under the certain circumstances. So the first thing you can do in order to develop a real gas equation is let's look at the assumptions behind the ideal gas equation. And we had a couple of them that we knew were a little bit dubious. So the first one is this idea that the volume of the gas is negligible. Okay, so if we take the ideal gas equation, we have it on this part of this. So what we need is if the gas is actually, if the volume of the gas is actually important, then it's going to shrink the overall volume or free space that the gas can move around in. And so we can represent that by subtracting the amount of the gas times some kind of, let's say, empirically determined parameter, reflecting that volume of the gas. Okay, so there's our B parameter. So we would correct that. So then the second assumption that we had that we knew was not very valid was there are no intermolecular interactions. Well, if intermolecular interactions are important, we need to correct for those as well. So we're going to keep our volume correction, and then we're going to put a second term, in here that accounts for intermolecular interactions. And so A is once again this empirically determined parameter given some units, and this unit of, I've put it in bar liter squared per mole squared. It could be in atmosphere liter, whatever units of pressure you have. Okay, and so what I just described for you is what we call the van der Waals equation, and it's actually the simplest real gas equation. And you can see I've written it again, or maybe a better way to put it is if we can remove the number of moles, so the extensive part of the property, and make it an intensive. And use molar volume, then the equation becomes this, where we have the molar volume minus B, and then this parameter over Vm squared. So A and B are these van der Waals parameters, and they turn out that you can either determine them, which of course we're not going to do by making lots of measurements, pressure, volume, temperature measurements, or you can look them up in a table. But the nice thing is at this point, as opposed to the ideal gas equation, these parameters are gas dependent, right? So now we're acting like chemists again. So nitrogen is different than oxygen. We all know that. But now we have that reflected in our gas equation. And typically this would work if you have high temperature and large molar volume. So if you took this and you had a high temperature, you'd make this would be unimportant. If you have a large molar volume, then the B becomes unimportant. You're going to end up, and you'll make this first term much larger than the second term, then you'll get fairly close to the ideal gas equation result. Okay, so it does extrapolate at the extremes to the ideal gas equation, which is important. And then there are several other types. There are multiple of them. There's like a Beatty-Bridgman. There's a van der Waals, a Beatty-Bridgman. There's another couple of them. The only other one we're going to kind of present here in terms of parameters is this Redlich-Kwong. It's another real gas equation. It's very similar, and you can see in form where we're accounting for the volume of the gas, and in this case is your intermolecular interaction parameter, but it's a little bit more sophisticated in terms of it. But once again, these parameters are also gas specific and found in, say, like table 7.4 in your book or in tables. So that's one approach to doing a real gas equation, is to come up with these parameters that are associated with each individual gas. Okay. Well, and that sometime, well actually, and I should backtrack then. So the Redlich-Kwong and the van der Waals equations, those don't fit all pressure, volume, temperatures over all pressure, volume, temperature ranges, right? So they don't, a gas does not always act like a van der Waals gas. It acts like a van der Waals gas under certain conditions. It acts like a Redlich-Kwong gas under other conditions. So these are also approximations similar to the ideal gas. So if we want to know the correct answer, right, we can do an approach, and this is one of the approaches that physical chemists will do. If if you need to understand the relationship between pressure, volume, and temperature, and you're willing to sacrifice the physical intuition associated with the equation, you can just fit it to a function. And then this is what I'm showing here is the virial equation. And it's just basically a power series. And any set of data can be fit to a power series as long as you expand it on a large enough amount of time. So what I have here is you have pressure RT over Vm. This is the ideal part, this first term. Then we add a correction to Vm squared. So we're expanding it as a power series in 1 over Vm. And we add a virial coefficient, B. Well, if that doesn't work, if that doesn't fit our data, well, then we add a third term. So that's C, and then we expand the expansion out to Vm cubed, and so on. So then we would have D and E and so forth. So you can get very, very large in terms of your power series if you need to fit it. The number 1 is actually your A coefficient. You notice there's no A there. We started with B. But basically, you can fit any set of data over all pressure, volume, temperature with a virial equation. The downside is that B, C, well, A, B, and C, the virial coefficients, they don't have any physical interpretation, right? So there's no easy way to associate B, for example, with the size or the volume of the gas itself, or C with intermolecular forces. It includes all of those factors, right? So this is just a way to fit the data to equation so that you could predict if you had this volume and this temperature, I know what the pressure is because I have the virial equation that tells me exactly what it is. So those are our real gas equations, and what we'll do is we'll work through some problems and see under some conditions where we would want to use the ideal gas equation, some conditions where we'll want to use real gas equations, and as we get into thermodynamics, we'll see that oftentimes the simpler equation is much easier because we can get more meaning out of it because of the math. Until next time.